Hello, everybody, and happy Monday. Today, we're going to work through a mathematical result that I find really interesting. It's about the binomial distribution. Right? What does binomial mean? Well, it just means anytime you have a heads or tails type outcome, up or down, left or right, you name it, kind of distribution, you have what's known as a binomial distribution. And so if you flip a coin, you get heads, 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 and tails, 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 etc. A binomial distribution is counting basically how many times you got heads and how many times you got tails. And that counting is useful. Now, why do we care about it? Well, we care about it because of cell division. As it turns out, when a cell is dividing, it's splitting up its proteins and it's splitting up its other components as well, but it's splitting up its proteins. And how many proteins go to one cell or another cell turns out to follow the binomial distribution. Now, if you didn't know anything about the binomial distribution and you were just hearing about it, the one thing I'd want you to stick in your head is it's about 50-50, right? Which is about what you'd expect, with results that skew one way or the other being fairly unlikely. So it's the kind of result that sort of looks like a bell curve. In fact, when we become continuous, we actually do become the Gaussian. But so it's a kind of result where that's your sort of 50-50 result. And then sometimes you get a few more heads, sometimes you get a few more tails, etc. And we're going to work through this problem. This is, warning, this is a very math heavy problem. Now, full disclosure, you're almost certainly not going to do something like this in your graduate career or whatever you do next, right? You might. If you're a physicist, you might see this again. If you're not a physicist, I want you to see it just because it's cool. It's a really neat calculation. It's a neat result. And it's one of those things that I think is kind of fun because you get to see math from a different point of view and realize, oh, there are some really neat and clever tricks. So this is based off of problem 2.7, which I've assigned on the homework, and I only want you to do, 2.7a, and then what's assigned in the rest of this problem, which, you end up getting to 2.7b, but I've given you a lot more scaffolding. Remember, our textbook is really intended for a more advanced student with some more techniques under their belt. So we have to give us these things. So, okay. What we have here, as I said, the binomial distribution, the probability that M occurs in some given time. So what are P and Q? P and Q are your relative probabilities of getting heads or tails, going to the daughter cell, staying in the parent cell, etc. And generally speaking, P and Q are going to be equal to one another. They're each going to be 0.5. And so this is kind of a really funny way to write the number 1. We're saying the probability of going left plus the probability of going right raised to the nth power, meaning you're going to do n proteins or n coin flips or something like that. And that's going to be the sum of probabilities of each of the individual events happening, right? All this is saying is add up all the possible outcomes. So as it turns out, if you want to actually figure out those probabilities, you can find it here. Now, I don't need you to worry too much about this. This is called combinatorics. You have actually seen this sort of thing before. You just don't realize that you've seen it before. You've seen it when you, in probably high school, wrote something out like this. And if you don't remember what that is, Pascal's triangle, it's what many people know it as, but this has been known since several thousand years ago in China. So this is a result that many people have found, not based off other people's work. They just sort of found it independently, which is really exciting that so many different people have come to the same result. Well, what is this thing? How do I use it? Well, let's imagine that I have like x plus y and I want to square it. Well, squaring it means go to this row. So that means that x plus y squared is going to be x squared plus, and you see the coefficient is 1 for the first term, that's x squared. 2 for the next term, well, this is going to be 2xy, and then 1 for the final term, so plus y squared. That wasn't too hard. We probably all knew that already from some high school course or some, prior math course. Well, now what if I have x plus y to the third power? Well, we know that when we multiply those all out, the largest single power we're going to get is the 3. And so we're going to get an x cubed. And that's going to follow this trajectory right here on this row. So that's going to be x cubed, there's only one of them, plus 3x squared y, plus 3xy squared plus y cubed. Now, I hope that that's clear. Whoever's in charge of kind of running the video, please pause, check with everyone, make sure that you understand what I'm talking about. And if not, please help each other figure that out. Okay, so pause now. All right, thank you guys for doing that. Pascal's triangle is basically what is in this kind of ugly looking mathematics here. You just don't realize that that's what's there. If you were to write this out, you see you get p to the m, p to the n minus m. And when you write, say we're going to write this out, and we're going to say big N is 2, or 3. We're going to do 3 flips. Okay? So I have a sum on m equals 0 up to 3. So that's going to give me 4 terms in my sum. And that's going to be, 3 factorial over 0 factorial, 3 minus 0 factorial. That's the first term right here. And then I've got as well p to the 0 and q to the 3. Okay. And then I have to do the next term in the sum, which is going to, the only thing that changes here is m gets 1 bigger. So now I do the next term in the sum. I've still got 3 factorial in the numerator. Now I have 1 factorial down below. And now I have 2 factorial here. And then this is now times p to the 1 q squared. Okay? And then I write out the next term. But I'm not going to write them all out, but there's going to be 4 in total. Maybe you see this already. This is 3 factorial divided by 3 factorial, which is just 1. Any number raised to the 0 is just 1. And then this is q to the 3. So this whole first term is just a fancy way of saying q third, which is what we had when we did x plus y cubed above. This is going to give you the exact same result. We can just actually write it out at this stage. It's q cubed plus 3p q squared plus 3p squared q plus p cubed. All right. And so again, this is the probability of getting heads, the probability of getting tails, something like that. Probability of going to the cell on the left, probability of going to the cell on the right. And if those probabilities are 50-50, then you're really just going to get what this says, 1/2 cubed. So you're going to get 1/8 here. Then you're going to get, in this term here, 1/2 times 1/2 and 1/2. So that's 1/8 again with a factor of 3. So now I'm going to get 3 over 8. I'm going to get the same 3 over 8 from the next term, and then 1 over 8 from the final term. And this makes us happy because 1 plus 3 plus 3 plus 1 is 8. Therefore, we're going to get 8 over 8, or we're going to get 1. So you might be going, wait a minute, why did we do all of that writing if we're going to just get 1 at the end of the day? Well, as it turns out, this is going to help us understand the distribution. What do I mean by the distribution? I mean, what is the average result? What is the variance? What's the likelihood that I end up with 60% in one cell and 40% in another cell? And why is that useful? Well, if you do a bunch of cell measurements, and how is this done? We take proteins and we give them fluorescent tags. So one of those is called green fluorescent protein. And that's because it's green when it fluoresces. So you hit it with some kind of blue light, and it glows green. Now, why is that? Well, because anytime you do fluorescence, you always take a higher energy photon in, and you emit a lower energy photon out, right? Because I can't get energy from nothing. So I get some kind of blue photon coming in, and I get some kind of green light coming out, because blue has higher energy per photon than green. So you mark your proteins in your cell with green fluorescent protein, and you watch it under fluorescent light, okay? And as it's fluorescing, you can see which cell the proteins go into. Now, I'm simplifying a lot of this stuff, but you can see which cells the proteins go into. And then you can take a measurement, and you can do this many different times. And what you see, what we find from this, is that cell division acts just like a binomial distribution, or maybe put a more accurate way, cell division can be described by a binomial distribution. And why does that matter? Well, a binomial distribution is one that just says you have two events, they have some appropriate probability, and you're going to get a pattern that we recognize, right? And so, if let's say you're looking at an even number of things, on your distribution, you're going to find that you're going to get, let's say you're flipping a coin 20 times. So that means you're going to, on average, have 10 heads and 10 tails, right? And so that's what I'm kind of showing here with this distribution. I'm saying, okay, the biggest number is going to be 10. Then, the next number, maybe 8 this way and say maybe 8 this way. Well, what does that mean? Well, if I get 10 heads here and 8 heads here, that means I got 12 tails. And if I got 8 tails here, that means I got 12 heads. The point is you've got some finite, limited number of outcomes that you're going to get. And you can do a lot of measurements and say, does my data look like this distribution? And if it does, then it tells you that pure randomness controls that cellular process. And so this math is really neat because it shows us that things like cell division, or at least parts of cell division, are purely coin flips. And as long as you have enough things that you're flipping a coin with, you get a nice, dependable average that is going to be physically realized. And so this is really neat. We have this illusion of volume at the macroscopic scale, right? When I walk up to a table and I put my hand on that table, we think, oh, it's solid, there's something there, right? But as you learn in quantum mechanics, and as you learn as you're studying atoms, 99% of that is empty, right? So that table is 99% empty space. But you don't fall through it, right? You're not falling through the chair. Why is that? Well, because when you have a very rare event, which is an interaction, times a large number of things, 10 to the 23rd atoms, you get a very dependable outcome. So every time you wrap your knuckles on that table, you're getting the averaged outcome of some number of your atoms strike some number of those atoms. You have an interaction, and you get the illusion that volume is there. Well, in the same way here, if we're looking at these processes and we're watching these cells divide and we're watching these proteins move around, it might feel like something is pulling them apart in different directions and like making this happen. The truth is, it's just probability. It's just a probabilistic interaction. And that's what this problem is all about. So I hope that my sort of selling it gets you interested in diving into this math a little bit. So again, for those who've got a solid math background, this might be a little slow, and just know that a lot of times when I'm talking about biology, other people in the class feel the same way. So instead of going speed up a little bit, find some compassion and maybe help some of your peers out with the math. And if no one's feeling like this math is easy, well, I'll be back soon. All right. So this right here is the probability of some particular outcome happening. And that's all we have here, which is just this term here, right? And so any particular, I'm going to get 1 head, I'm going to get 2 heads, I'm going to get 3 heads, etc., all the way up to n number of heads, right? If I flip a coin 10 times and I get 10 heads, that seems pretty unlikely, but it is something that could happen, and that does contribute to the probability. And so if I add up the probability of all individual events, I get 1. So if you get yourself a little lost, just remember the answer is always 1. Now, the caveat I have to give you is as follows. It may be tempting that anytime you see this in the problem, you just make it 1. Do not do that. You will get the wrong answer, and this problem will be worse than it should be. The last thing you're allowed to do is to simplify by saying that is equal to 1. And hopefully we'll see why in just a moment. So if I have this as my given probability distribution, and this is just a number, right? Just a number between 0 and 1. If this is my given probability of any particular event happening, as it turns out, I can use something like this to get the average outcome. So if you look here, and we just kind of cover up that m per minute, this right here is just that particular probability that we'd expect. And this m is an individual result, 3 heads, 8 heads, whatever. This is a weighted sum, weighted meaning weighted by the probabilities, right? This is the outcome. You can imagine this very simply. If I have a six-sided die and I were to roll it, one of the results I could get on that die is a 1. What's the likelihood of that happening? 1/6. Another outcome I could get on that die is a 2. What's the likelihood of that happening? 1/6. Another outcome I could get, right, is 3, 1/6, right, plus 4 times 1/6, plus 5 times 1/6, plus 6 times 1/6. And if I add all of those up, I'm going to have the exact result that I have here. And this is going to be 21 over 6, which is 3.5, which is the average result anytime you roll a six-sided die, which could also be found by adding the lowest number to the highest number and dividing by 2. So the lowest number you can roll is a 1, the highest number is a 6, add them up, you get 7, divide by 2, you get 3.5. So the reason I'm giving these examples is just to say this looks like wild, crazy math, but it's really not. It's just a way of writing something you know how to do in a more complicated fashion. So the thing that most of you have less familiarity on is called m squared, right? And this is called the second moment of your probability distribution. This is you take the m squared value and you do the same weighted sum. And this is going to give you a little bit of a different kind of answer. This is most notably different if you have positives and negatives in your potential outcomes. So let's say you made heads +1 and tails -1 or something. This m squared is not going to care about that. It's going to square everything and add them up. This is actually going to give you an idea of how far spread out your results are. So think about it. If I've got an equal likelihood of positive results and equal likelihood of negative results, and I square them and I add them up, I'm going to get a fairly big number because what used to be -3 up in this result and would reduce the total of the sum, that -3 squared is going to be 9, and it's going to enhance the value of the sum. And so this is telling you really just how far spread out these values are. So this is just background. This is just preamble. Okay? And what I want you to do is to verify this result. All right? And this, just like I was saying a minute ago, is a really neat math result that we're going to use because it's really cool. And I'm going to now show you kind of how we do that. Now, you are, of course, free to just kind of copy down what we're doing, but that's not really teaching us anything. So I'm going to ask you instead, write if you need to. If that's your jam, you need to write it down. Remember, fine, write it down. But otherwise, I want you to just sort of follow what I'm after. What am I doing here? Well, here's the verification we're doing, right? We are saying, okay, find the average result of a coin flip. That's a weighted average right there. And hopefully you all realize that getting together in the classroom and listening to this together kind of forces you to keep moving. Because when we watch videos that are harder and more complicated, sometimes we want to turn on some fluff. So hopefully everybody's doing okay here. And so this is just calculate that weighted sum. Now, if this m were not here, this would be super easy to do. We would know that that was 1. So the point is we want to try to get rid of this m and turn this sum into something that we know. Turn the sum into something that's easy to do. Well, let's just take a look now at what we have. We've got m p to the m, right? That's this m, that's this p to the m. And the question is, can I do anything to get rid of this particular value to make my life a little bit simpler? Well, we're going to do something that's probably never occurred to you, right? However, I'm going to give you a hint. Let's imagine you saw 3x squared, and then you saw 4x cubed, and then you saw 5x to the 4th, and 6x to the 5th, etc. You would go, oh, those are just derivatives. And I'd say, yup, that's right. Those are just derivatives. However, your intuition may not work as well if you saw this. And why is that? Well, because the numbers aren't exactly right. The pattern isn't exactly right. Right? It's almost what it should have been, but it's not because, that prefactor is now wrong. However, if I just make a really subtle change and I do 2x, 3x squared x, 4x cubed x, 5x to the 4th x, suddenly you're like, oh, Right, derivative, and that extra thing. Well, that's what we're going to do. We're going to recognize this as being m. Come on, eraser. This is m, p to the m minus 1 times p. Now, you might say, what are you even doing? Why would you do that? And the answer is because you get the right answer. Right? When solving a problem, it makes it a lot easier if you know what the right answer is. So the truth is, nobody solved this the first time this way. Instead, they solved it and they got sick of doing it and they wanted to do it an easier way. And so they found another way. And that's where I think a lot of math comes from, is people not wanting to do something hard. So they invent something that looks harder, but it's actually easier. So if we now look at this result that we have, we go, oh, I know what that is, right? That's just the derivative of p. Great. So I'm now going to write this as p partial with respect to p, pm minus 1. Now it's possible that when I just said that word partial, you said, what's a partial? Well, this right here isn't exactly a derivative. I mean, it is, but it doesn't look like what you've seen, right? What you've seen before is this d dp. And this isn't just like poor penmanship. It's a slightly different thing. Partial derivatives are when you have at least two independent variables, and I can't just take the derivative of one of them. Or I'm sorry, and I want to just take the derivative of one of them. So let's say I have a function f of x and y, and I want to take its derivative. Well, because there's two variables, I have to do that carefully. I either have to take the derivative with respect to x, that's what this partial means, or I have to take the derivative with respect to y, and again, that's what that partial means. And so I really want to invite the rest of the people sitting in your class right now to pause this video and to ask your peers, what the hell is he saying? And I know that that's hard to do, right? I know it's hard to say, everyone else is nodding their head, I don't know what's going on. But like, this is your life, man. Take control of it. If you don't make the space to learn stuff now, when are you going to do it? Right? How many times have you said, I'm going to go home and look at that, and then like, you don't? So take control. Say, someone pause it. What the hell is this guy talking about? Who cares? Get that help. So when I want to take the derivative of a function of two variables, and I only want to look at how one of them changes, I do what's called a partial. And that partial says treat the other variable as being constant. So let's imagine f of x, y is equal to x squared y. If I take the partial of f with respect to x, what I'm doing is saying only x is changing, treat y like a constant, and so what I would then get is 2xy. If instead I took the partial of f with respect to y, I would just get x squared, because I'd only be taking the derivative of y. All right? So hopefully you can at least follow this along, even if it is brand new material. I don't think it's that different from stuff you already knew how to do. So we're now going to say, look, I want to be able to do this sum, but I can't do it right now because I have this stupid m in here. So if there's a way I can get rid of that m, I'm going to do it. And we see that m, pm, can be rewritten as p times ddp of p to the m minus 1. So now I go back and I look at this piece, and this is the next step. And I see I now have p to the m ddm of this whole thing. Now what's wonderful about this is we know this whole thing, because of what we saw above, or what we saw here, sorry, this whole thing here is just p plus q to the n. Now you might say it's also 1, but again, 1 is the last step. 1 is I'm done with the problem, I'm going to plug that identity in and then see if it works. All right? So now we go back up here and we realize that this whole thing right here is nothing but p plus q to the nth power. And so now what I have PDDP acting on that. And this is a function of two variables, those two variables being P and Q. However, because it's a partial derivative, I only care about how P changes, not about how Q changes. So when I now take that derivative, well, I'm going to just do it in steps. I'm going to get P n P plus Q to the n minus 1, right? That's the derivative. And then I take the derivative of the inside, and the inside is just that P. dP dP is just 1, so this is the result that I get. And so I took this kind of ugly-looking sum, I took its derivative, and then I was able to evaluate it as that. And now when you look at that, you say, okay, there doesn't look like there's a lot more left for me to do. This is just 1. So the answer that I get is Pn. So what answer did I just get? The question was, what is the average result after doing n flips of this probability distribution? And as it turns out, it's a fairly understandable result. If P is a half and n is, say, 20 coin flips, then the average is going to be 10 heads, and then the other result is tails, and 10 tails. Okay? So nothing remarkable here, right? It's not like we've just said, wow, look at this amazing math result you've never seen before. It's just you found an answer that you hadn't done, through a method you hadn't done before. And that's really what problem 2.7 is teaching us about today. It's how to do this stuff. So your question is to basically answer what's going on here, which is going to help you do problem 2.7. But again, I'm having you do it through a slightly different method. All right? And that's what 2.7 is all about. And then 2.7b is now talking about GFP and daughter cells and talking about how to make sense of what's going on. And you're going to use the results from 2.7a here. This is, to date, the most mathematically rigorous problem that we've done. This might take you 2.5 or 3 hours to do well. But I think it's really, it's time well spent. And obviously you're allowed to work together. But I need each person to be able to explain their results. And this kind of question is one I've asked about during that final exit interview because I find it so much fun. So hopefully we get somewhere with that. All right. We also had a reading assignment for today. And so what I'm hoping now is that you all will pass around the reading assignments like we've said before. You will then kind of pause the video, read through stuff, sort of talk about them. Okay. And these were the reading questions that I had wanted you to talk about. Now, so I'm going to assume that you have already talked about everything and you are replaying the video. If not, pause it here. Okay. So one of the questions, this first question is, how's the life cycle of a phage compared to a virus? And I purposely chose this wording because I found it so odd. One of the most prominent conferences that people have is the virus and phage conference. And I always go, why are we doing that? Phages are viruses. And I think it's just a historical designation. People just are used to calling phages phages and not phages viruses. And what, I don't know. I don't really have a good answer where it comes from, but I wanted you to see it so you wouldn't be surprised by it later and say, wait a minute, I thought phages were viruses, right? The primary difference, of course, is that phages generally don't enter the cell intact as capsids because they're just too big to get inside. So phages generally have to find a way to get their genetic material inside of a cell without entering it. And that's just due to size and volume restrictions. But once they're inside, things are pretty similar, right? Things are pretty similar. All right. Some notes. roughly how long does it take for a bacteriophage to finish its life cycle? Hopefully we've talked about that. We understand what's going on there. Question 3 or equation 3.16. What is that trying to say? Let's see here. I think I have the book open. Maybe I don't have it open. Uh-oh. Okay. See, if I was better at editing, I would then, go edit that sort of thing out. And sorry about that. I guess in a normal class, you watch me hobbling around back and forth. So, yeah, this is about the same. All right. I assume right now somebody's going, does he actually expect us to watch all of these? And that's possible. And the answer is, I hope so. I went through the trouble of recording them, but we'll see what happens. Okay, so 3.16, come on. This is that flagella motor that we have printed in class. I'm just going to go on a sidetrack for a minute, right? And this thing spins, up to 6,000 RPMs. It's pretty amazing. And this is a very rigid filamentous piece here, and this whole thing gets turned like a dough hook. Just blows my mind. When we say, bushing, drive shaft, rotor, those terms are not accidental. They are quite purposeful because they act just like that for these processes. So, okay. So let's see. I'm after equation 3.16. Okay. Explain 3.16 and what it's trying to say. All right. So this is talking about reaction rates. And so this is an exponential decay, right? An exponential breakdown, or an exponential weighting factor, depending on sort of what you're trying to talk about. These values might change a lot. They might not change a lot. This is talking about basically a free energy barrier that we're trying to get over for something to happen. And so we talked about this earlier in the class. We said, okay, here I have this kind of wacky looking potential. What does this thing really look like? Well, here we're talking about what's the likelihood that thermal fluctuations are going to take me from one of these places here to one of these places there. And so that thermal fluctuation, is going to depend on how much energy I have, how high this barrier is, and how likely it is to occur. And then sometimes we're able to add enzymes that lower that barrier, making it sort of much easier to happen. And so in this sort of case here, putting this barrier or enzyme sort of drops the energy of the system and allows that transition now to be much easier to get done. Sometimes this variable here, which isn't really physical, right? It's not like you're at 3 meters away and then you're at 5 meters away. This is called a reaction coordinate. And this is just a way of tracking, how far along the process is. So you might say this is 0 and this is 1. So if your reaction coordinate is 1, you know that your reaction has occurred. If your reaction coordinate is 0, it hasn't yet occurred. That's what this is all about. So 3.16 is saying that the higher that barrier is, the more this term will suppress what's happening. Why is it suppressing it? Because this is e to the negative something. So it's 1 over e to the positive g barrier over kBt. If you haven't encountered kBt before, in other courses, this is a term that means energy. So kBt literally is energy. This is Boltzmann's constant, which is basically some number of joules per Kelvin. And then you plug in your temperature. So you're going to get now just straight up joules. This is a unit of energy that you have available to you. Now, if you have seen any physical chemistry or anything like that, you may have learned that for every degree of freedom that a molecule has, it will thermalize and have 1/2 kBt of energy. What does that mean? Well, if a molecule can move in 3 dimensions, x, y, and z freely, we would say it has 3 degrees of freedom. And so at 3 degrees of freedom, you would get a half kBt per degree of freedom, or your thermal energy would be 3/2 kBt. And I suspect that's a result many of you have seen before. And then if you get into any kind of chemistry that talks about rotational bonds, that number sometimes climbs to 5/2 kBt, but it's all coming from the same thermal distribution. And so what's happening is this exponential, which has to be unitless, right? Why does it have to be unitless? Well, I can't have exponential meters, right? I wouldn't know what that meant, right? So I can't have exponential joules, right? That doesn't mean anything in and of itself. So we know that this whole thing has to be unitless, or I can't take the exponential of it. And now that kBt, or that GB, is this energy barrier. And how strong is energy barrier? Well, it's being modded against the kBt energy scale. Okay, that was a lot. Long story short, if this term gets small, right, that means the reaction rate is going to be small. What makes this term small? When the barrier height gets high. Okay, what makes this term bigger? Well, inversely, as temperature grows, you have more thermal energy, and as temperature grows, that reduces the effect of that barrier as well. So this is, if you hadn't seen this, now you have. You can begin to understand free energy diagrams and what it takes for reactions to occur. All right. As your free energy or your kBTs are growing, that's putting you higher and higher up here. And we're going to see a case of where the ideal gas law comes from and its relationship to free energy sometime next week. Okay? All right. Back to the reading questions here. What is the story of figure 3.3? Write a few sentences summarizing this process. Okay. And so, this is what we were just sort of talking about here. We have, some state where there's something holding it closed. The enzyme would make it so that the holding of that spring between this state is lessened. Therefore, thermal fluctuations are more likely to break it apart. Okay? And just like think of a simple example. You've got, if you ever dropped like dish soap into an oily surface, right? It kind of spreads it all out. You can almost think of like the dish soap as enzymatically helping you separate something. I mean, this is a stretch, but the idea is that it's reducing the pull or the hold. It's interfering with the normal chemistry that makes the thing hard to do, but it's not causing itself a chemical reaction to occur, right? That's what an enzyme's all about. So this story is really just about how enzymes not only lower the free energy curves, but they lower the relative barrier in between those two different wells, making reactions easier to happen. Okay. One of the units in equation 318, the units in equation 318, which, again, so as we're passing through here, here's kBt, right? This is just Boltzmann's constant. Boltzmann's constant divided by Kelvin, multiplied by Kelvin, and you get some energy scale. However, you'll see that this energy scale is like ridiculously small and kind of tricky sometimes to manage. So in this case here, these authors chose to make it piconewtons per nanometer to give you a number closer to 1. When we do atomic physics, we often work on an energy scale of EVs or electron volts because that gives us numbers that are close to 1. Nobody likes to play with numbers that are like 10 to the minus 21. That's just a nuisance. Okay. So now, we're saying, okay, here we go, 318, and I'm saying, what are the units in this equation? What are we dealing with here, right? D is some diffusion constant. This is saying how long is the standard time scale for diffusion to occur, right? And so X, right, is just some distance that I'm migrating over divided by this diffusion constant. And we're saying, what is that appropriate thing? Well, I have to get the units of time, right? So this is going to be meters squared or length squared. Therefore, this has got to be some kind of meters squared per second.
so that I get the appropriate units of seconds here. And we're going to play with this a bit more when we do some fluid dynamics a little bit later in this course and kind of understand better what we mean when we say diffusion. But what we can do here is we kind of look at, estimates moving proteins around. Imagine I've got a cell and I've got proteins in it, and I want to know how quickly those proteins diffuse or migrate through the cell. That is what this example is sort of talking about here. Okay. Estimate the stepping rate for myosin in figure 3.33 is the next one. Let me actually say just a couple more words here about this because I can't but help myself in doing that. E. coli is a really fascinating little entity. It has a nose, like technically on its different ends, it has receptors that are able to encounter small molecules, basically as if smelling. It's able to detect its food. But here's the part that's really wild. If you watch E. coli swimming through through a media, and you can tell that it's smelling food. It's going, okay, there's food, and it's eating this food, it's eating this food, it's eating. It will turn on a time scale that's faster than it can process the smell. And so let me say that again. Imagine it took 1 second for it to be able to smell, oh, there's food in front of me. It will turn in a half a second. And so you might say, well, if you're not going to use that information of smelling, why smell? Right? Do you understand what I'm after? Like, why bother having a nose that tells you when you run out of food if you're not going to use that information? Well, as it turns out, it does use that information, but not in the way that we expect it to. And so what it does is it's sniffing ahead of it, going, okay, food, 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 keep eating, keep moving, keep eating, keep moving. But E. coli basically has a cellular mechanism that says once it's gotten enough food, expect things to go wrong. And so after it has smelled food continuously for a period of time, it will just spontaneously change directions. And this is purely a probabilistic type buildup. And so it's not smelling to know when it's run out of food. It's smelling as a way of tracking how long it's been successfully eating. This stuff just blows my mind. Every time I learn something new about cellular processes or E. coli or something like this, I go, really? That's how this evolved? So it's like, oh, things have been too good for too long. I'm going to change. And it just blows my mind. It just blows my mind. All right. Well, I have just found out that I have people here to see me. So I'm going to wrap things up a little bit here. I'm going to talk just quickly about 3.33. And hopefully you guys can work on 3D printing project, after we're done. I have actually met one of the people that has made videos of these little myosin walkers. I have the Kinoshita lab, which is posted on Moodle, shows videos of these things moving. And he's a really fun guy. I met him at this summer workshop I was at in Corsica. And he just, one of the most joyous people we've ever met, and loves nothing more than making videos of little tiny molecules moving. And so we have this stepping rate. So what's happening here, right, is he's able to basically put fluorescent markers. Fluorescent markers is everything. He's able to put fluorescent markers on these myosin walkers and time how long they are given at a given location. So we can see here that the position isn't changing, right, for some number of minutes. And then it steps. And then it stays there for a period of time. And then it steps. And then it stays there for a period of time. And then it steps. And if you look here, you see that this is not a uniform time step. What do you think you're going to find if you were to do a histogram of all these little time steps? You're going to find a nice average. You're going to find a nice distribution. And you're probably going to find that it's a probabilistic step. Okay, everyone, I hope you're doing well. I should be out of surgery. I should be off painkillers. If you've got questions on homework, please do send them to me on Teams. I can't promise I'm going to answer you right away. I don't know how well my brain's working at this point, but I do want to talk to you. Thank you so much for making this work and helping me make the space to have my surgery. I'll see you all soon. Have a great rest of your day. Goodbye for now.